Greetings. When you start messing around with more complicated momentum problems, you will in all probability find that you have to use energy considerations. And in the problem, you will have to decide where you can use conservation of energy and where you can't. And for that matter, in the problem, you will have to decide where you can use conservation of momentum and where you can't. Along with that, you really should be able to justify the use of both of those. What you're about to see is going to be the analysis of a fairly complicated problem in which both of those issues are going to be taken up. So, enjoy. So here's the setup. You have an artillery cannon whose mass is known. It fires a shell of known mass with known muzzle velocity at a known angle. And the cannon, which is on wheels, is attached to a spring, which is attached to a wall, the spring constant. And when the shell is fired, the cannon is going to recoil. It's going to elongate the spring some amount. And the question is, by how much will the cannon move when the shell is fired? So what kind of things do we need to notice about the system in trying to analyze it? To begin with, before the firing, it's important to notice there's no mechanical energy in the system. Mechanical energy is the sum of the kinetic energy and the potential energy. There is no potential energy here. The energy that motivates this shell up the barrel is energy, it's non-conservative work being done by the releasing of chemical energy. Chemical energy produces non-conservative forces. They do not have potential energy functions. There's no mechanical energy in the system to start with. There is no initial momentum in the system. Nothing is moving to start with. After firing the shell, there is mechanical energy in the system. The shell has kinetic energy. It's moving. It's some distance above its original height, so it has gravitational potential energy. The cannon itself is in motion in the x direction. As time proceeds, the cannon will move outward, the spring will elongate, so you'll be getting spring potential energy, and in fact, the kinetic energy of the cannon will actually turn into spring potential energy. But at least initially, as the shell is emerging from the barrel, the spring will not have elongated appreciably, and pretty much all of the energy wrapped up in the cannon is going to be kinetic. There will be a component of momentum for the shell in the x direction. There will be momentum for the cannon in the x direction initially. There will also be momentum in the y direction for the shell. And as I just said earlier, if you simply look at just what's happening with the cannon is going to end up initially having kinetic energy. It's going to turn itself into spring potential energy. Using that observation, we can ignore the shell altogether and look to see what's happening with the cannon as far as energy goes. Just after the shell is left, the cannon will have all kinetic energy. It turns itself into all spring potential energy, which means we now have a relationship that relates the maximum displacement of the cannon, which is to say x here, and the spring for that matter, and the velocity of the cannon just after the shell has left it. To figure out what this velocity quantity is, we're going to have to take a look at momentum considerations. So this is where things could potentially get a little confusing. To begin with, you have to figure out what time interval you want to take a look at. I'm going to take a look at the time interval delta t that goes from just before the shell is fired until it has just left the cannon. The explosion itself is going to produce an impulse which is going to motivate the shell up the barrel. It will produce an equal and opposite impulse on the cannon, which will effectively motivate the cannon in this direction. If the cannon was out in space, it would have motivated it in this direction, but there happens to be a really large normal force acting here between the ground and the wheel. And so the net effect is that you're going to end up getting motion in the x direction but not in the y direction. The point, though, is that the explosion is going to end up producing an internal impulse, which is not going to end up affecting what's happening with the momentum along the x-axis. There will be a component of gravity along the displacement of the shell as it goes up, and in fact that will produce an impulse. Fortunately, the time interval during which the shell moves up the barrel is going to be so small that for all intents and purposes we could pretty much ignore that impulse. And friction is going to end up producing an impulse as the shell goes up the barrel. Two things. Number one, the time interval again is going to be so small that that impulse is really going to be negligible. But even if it wasn't, the impulse that the barrel ends up applying to the shell that's frictional is going to be equal and opposite the impulse that the shell applies to the barrel that's frictional. Those are internal impulses. Again, that shouldn't affect the net momentum in the system over time. So if we take a look at the cannon shell system in the y direction, there is no momentum in the system to start with in the y direction. After the cannon is fired, you have momentum of the shell in the y direction. Clearly, if you had none to start with and you ended up with some, momentum has not been conserved. And this is exactly what we expected. I mentioned earlier that the normal force is providing an enormous external impulse to the system in the y direction, changing the momentum content in the y direction. Again, momentum is not conserved in the y direction. Still, just for the amusement of it, I've written out the impulse relationship, or the conservation of momentum relationship. No momentum to start with, some momentum to end with. How so? Because there's all sorts of external impulses happening in between over the time interval. As I said, this is not useful to us. I've just thrown it in just so you can see it. So now we're looking at the momentum in the x direction. No momentum to start with in the x direction. Momentum of the shell in the x direction after the firing. Momentum in the negative x direction of the cannon after the firing. Assuming the time interval starts from just before the firing until just as the shell is leaving, which is to say before the cannon actually starts to elongate the spring. Through that time interval, there'll be no appreciable external impulse acting in the x direction, which means momentum in the x direction will be conserved through that interval. Writing out the momentum relationship, the x direction, no momentum to start with, no appreciable impulse in the x direction over the interval. Final momentum of the shell in the x direction, final momentum of the cannon in the x direction. Doing the math, coming out with a velocity of the cannon in the x direction of 2.4 meters per second. With that bit of information, we can now go back to our conservation of energy relationship that we derived earlier, put in the information that we now know, and from that we can determine that the cannon is going to elongate the spring by somewhere around 1.4 meters. So, relatively complex problem, a lot of stuff going on, but as you can see, if you just think your way through it, certainly doable. Anyway, that's it.